Al preguntarnos qué es nanotecnología, debemos pensar en algo muy pequeño. ¿Pero cuán pequeño? Un nanómetro es una millonésima de milímetro. O podríamos decir que es la mitad del ancho del ADN. ¿Y por qué es importante manipular la materia a niveles tan pequeños? Esto cobra mucha importancia si consideramos que a los 70 nanómetros las nanopartículas pueden ahondarse en los tejidos pulmonares, o que una partícula de 50 nanómetros puede introducirse en células, así como partículas tan pequeñas como de 30 nanómetros pueden atravesar las barreras del torrente sanguíneo en el cerebro. La nanotecnología no es entonces una rama novedosa de la investigación, cuyas aplicaciones suenan distintas o triviales. Es de hecho una alternativa para solucionar grandes problemas a nivel mundial.
Let's talk about the scale first. Well, there are some, let me use this slide. Let's start from here. About 1 meter, we are talking about humans. As you go up, well, you see the car, a killer whale, aircraft carrier. You can go all the way to a kilometer, which is about, a few kilometers will make the campus-wide length scale. Coming down, a laptop is about 50 centimeters, 30 centimeters wide. A butterfly is about a few centimeters. Then if you come down to about 1 millimeter or so, right below 1 millimeter, we'll come to resolving power of our eye. We cannot see anything clearly below that range. But if we go down at about 30 micrometer, we see a typical cell, a cell in a body. That cell is a living organism by itself. There are so many small parts of it. If we keep going, nucleus of cell is close to 1 micrometer, and they can all be seen if we use the microscopes. These microscopes will help us because we can use the light, the power of light, which has the wavelengths in the order of maybe half a micrometer or so. At this point, we come to a limit. Below that, we begin to see difficulty. Nature does not allow us to go down without additional insight, additional help from other technological advances.
The simplest thing you could do is take something like, say, chewing gum or nail polish would be something that you put it on a little glass cover slip and you push it over you pull it over an array of pillars, and just the action of your hand sweeping over the surface on these small pillars, fluid mechanics will take over, and the wobble of your hand will be small, insignificant compared to the fluid mechanical forces, and rapidly these thick films of material off of here will form into thin fibers. Now, this additional thing I'm showing here is we're starting with, instead of polymers, which is what nail polish is, we're starting with not nail polish of polymers in a volatile solvent. Now we're starting with a monomer and an initiator to cause polymerization. Maybe not of great interest to you guys at this point, but the point is we happen to be doing this, and the results I'm showing are doing this specifically with thrombin initiator and polymerized fibrin fibers, which we just got such beautiful results.
In certain areas like energy, the whole world is thinking about it, so you can benefit from their thought process too, but you have certain energy resources that are more unique or more applicable to your environment. So define the problem and then look for the hammer. And that's nanotechnology, and maybe it's not nanotechnology in certain applications, but defining the problem. If you see in my presentation, we defined the problem. We wanted to find these cancer cells. That was the problem. That drove the solution. It wasn't the other way around. We didn't develop a chip and go around that, let's find an application for this chip. We defined the problem and then solved it using, turned out to be nanomicrotechnology was a good solution for it. So that's number one. Use your environment to your benefit, define the problem. You can do it better than anyone else, given your unique composition. The next one is university can be very effective in helping you, the young minds, to define those problems, and university can actually define some of those problems. The other role for universities is training the workforce. If you don't have the workforce, who's going to solve those problems? You really need the workforce. You need to have people who are trained in sound engineering, physics, and chemistry principles, who also have, in this case we are talking about nanotechnology, who do have a good understanding of nanotechnology and its potential. You need to be able to generate that kind of workforce in order to have an impact in the field. And that workforce has multiple layers. Undergraduate education is very important, but I tell you, I hope I made it very clear in my presentation, higher level postgraduate education is equally, if not more important, in these kind of areas. You need the PhDs and doctorate students who are going to a whole different level of innovation where they are really surpassing their own mentors and professors in knowledge generation. They become the world's foremost expert in that area.